22nd of February, 2007. The Ross Sea, deep in Antarctic waters. The New Zealand longliner San Aspiring is targeting Antarctic toothfish when one of the longlines comes up with something wrong attached to it. The crew's initial estimate is 8 to 10 meters, roughly 450 kilograms. A colossal squid, Mesonychoteuthis hamiltoni, barely alive, still gripping the longline bait with its tentacles. They haul it aboard, photograph it, freeze it whole, and ship it to Te Papa Museum in Wellington. Scientists thaw it months later and measure it properly. Total length, 4.2 meters. Mass, 495 kilograms. The discrepancy between the deck estimate and the measured reality is worth sitting with briefly, because it runs through this entire subject. In cold, dark Antarctic water, things look larger than they are, but they also genuinely often are larger than anywhere else on Earth. The 2007 squid is the heaviest invertebrate ever directly measured. It's also one data point in a pattern that runs across dozens of unrelated species, from crustaceans to cnidarians to mollusks to mammals. The tendency, in the coldest and deepest water on the planet, toward unusually large body size. The mechanisms behind that tendency are still being argued in peer-reviewed journals. The pattern itself isn't. Start at the bottom of the scale and work upward. The giant isopod, Bathynomus giganteus, is a pill bug. The woodlouse you find under a garden stone reaches 1 to 2 centimeters. Bathynomus giganteus reaches confirmed lengths of 50 centimeters and weights approaching 1.7 kilograms, living at depths between 170 and 2,000 meters. A 76-centimeter figure circulates in popular press accounts. Multiple specialist summaries explicitly note that this originates from a non-scientific source and is unverified. The 50-centimeter maximum is the largest confirmed specimen, already 25 to 50 times longer than the most familiar land relative. In Exuma Sound in the Bahamas, the densest concentrations of these animals occur precisely where the temperature is lowest, between 3.25 and 13 degrees Celsius. Move to the open water column. Lion's mane jellyfish, Cyanea capillata, is a cold water specialist. Individuals from warmer, lower latitude waters typically carry a bell of about 50 centimeters and tentacles a few meters long. Northern, colder individuals can reach bell diameters exceeding 2 meters. A specimen that reportedly washed ashore in Massachusetts Bay in the 1860s had a bell 2.1 meters across and tentacles measuring 36.5 meters, 120 feet. That record rests on a single 19th century account with no documented methodology, and species identification has never been definitively confirmed. But even setting aside the maximum, the latitudinal size gradient in this species is well documented and consistent. Colder individuals substantially larger. On the Antarctic seafloor, sea spiders. Pycnogonids are a strange class of marine arthropods, mostly tiny, a few centimeters across in temperate zones. The Antarctic species Colossendice colossea reaches leg spans of 70 centimeters in water, hovering around negative 1.8 degrees Celsius beneath the ice. Most species worldwide are measured in millimeters. These Antarctic giants are 14 to 70 times larger than their temperate relatives, depending on the comparison. Go deeper. Past the continental shelf and into the abyssal zone, the supergiant amphipod, Alicella gigantea, reaches body lengths of 34 centimeters at depths between 3,890 and 8,931 meters. Most coastal amphipods are under 30 millimeters. Alicella has been filmed alive at over 5,300 meters in the North Pacific, a crustacean roughly 11 times the length of its shallow water relatives. Antarctic krill, Euphausia superba, reach 42 to 65 millimeters as adults, about 2 grams. Tropical pelagic euphausiids typically run 7 to 30 millimeters. Krill aren't the largest krill species on Earth in absolute terms. Some deep-sea euphorsiids exceed them, but as a direct comparison between polar and tropical members of the same ecological guild, the size difference is consistent and real. The pattern holds across phyla that share no recent common ancestor. The question, which has occupied marine biologists since at least the late 1990s, is why? In 1999, Gautier Chappell and Lloyd Peck of the British Antarctic Survey published a paper in Nature that became the most cited work on this problem. Their data said 1,853 species of benthic amphipod crustaceans from 12 globally distributed sites, polar to tropical. Their conclusion: maximum potential body size correlates strongly with the dissolved oxygen content of the surrounding water. Cold water holds more dissolved oxygen than warm water. In the Southern Ocean, deep upwelling keeps oxygen levels high and temperatures near freezing, which means the ratio of oxygen supply to metabolic demand tips in favor of larger bodies. Chappell and Peck argued this relaxed ceiling, not temperature per se, is what allows polar animals to grow beyond the sizes achievable in warmer seas. The logic is mechanically coherent. As body size increases, the distance oxygen must travel from an animal's surface to its deepest tissues grows faster than the surface area available to absorb it. In warm water, with elevated metabolic demands, a large body struggles to keep internal tissues supplied. In cold, oxygen-rich water, that constraint loosens. Larger body sizes become physiologically viable. This framework attracted significant attention and significant challenge. In 2013, Wilco Verberg and David Atkinson published a paper in Functional Ecology, pointing out that oxygen solubility and oxygen bioavailability aren't the same thing. Cold water holds more dissolved oxygen, yes, but cold water also reduces oxygen diffusivity, the rate at which oxygen moves through water and across biological membranes. The higher concentration is partially offset by slower delivery. The actual oxygen reaching an animal's tissues may not be as elevated as the hypothesis assumes. The experimental results haven't been consistently kind to the simple version of the hypothesis either. H. Arthur Woods and colleagues tested Antarctic pycnogonids in 2008, measuring how body size interacted with oxygen performance. Their finding: large-bodied individuals weren't more sensitive to oxygen reduction than small ones. In 2019, Caitlin Shishido, Woods and co-authors published a more rigorous version in Proceedings of the Royal Society B, testing 2 genera of Antarctic sea spiders across a range of temperatures. Again, no body size by temperature interaction of the kind the oxygen hypothesis predicts. The authors stated directly that their results don't support the predictions of the oxygen temperature hypothesis. Pycnogonids are the ideal test organism for this idea. They have no specialized respiratory organs. Oxygen moves directly through their cuticle by diffusion. If the oxygen hypothesis applies anywhere, it should apply here, and the experimental data keeps not supporting it cleanly. Woods and Amy Moran reviewed the entire hypothesis landscape in 2020 in Integrative and Comparative Biology, organizing competing explanations into 8 categories. Their summary: no clearly dominant single-factor explanatory mechanism or process has emerged. The second broad explanation involves temperature and metabolism. Cold temperatures slow metabolic rates in ectotherms, reducing the energetic cost of maintaining large body mass. An animal in near-freezing water burns through reserves more slowly, sustains longer growth periods, and can reach greater eventual size before the maintenance cost becomes unsustainable. This is the physiological basis for applying something like Bergmann's rule to cold water ectotherms. Carl Bergmann described the body size latitude tendency in 1847 originally for homeotherms, birds and mammals, where the thermodynamic logic is clear. A larger body has a lower surface area to volume ratio, loses heat more slowly, and is advantaged in cold environments. Extending that framework to cold-blooded marine invertebrates that don't generate their own heat is a different proposition, and the evidence reflects this. Marine copepod body size decreases roughly 45% across a temperature range of -1.7 to 30 degrees Celsius, with temperature as a strong predictor, but food availability explains equally as much variation in that dataset. Southern ocean lanternfish generally show larger sizes at colder, higher latitude water, consistent with a Bergman-type pattern, but species living in thermally uniform deep water show no significant size-temperature relationship at all. Freshwater fishes of North America mostly show the reverse of what Bergman's rule would predict, smaller at higher latitudes, not larger. The lizard genus Lialemus, examined across hundreds of species in a comprehensive phylogenetic study, shows no predictable increase in body size with latitude or elevation. The third hypothesis, reduced predation pressure at depth and in polar regions, is the least empirically developed. Some brachiopod studies in polar shallow waters are consistent with it, but quantitative tests are sparse, and the mechanism applies most logically to prey species. Sperm whales, apex predators, don't fit it at all. A fourth factor keeps appearing in the literature, sometimes with more explanatory power than any of the first three: food quality. The intense seasonal phytoplankton blooms of the Southern Ocean, a massive burst of productivity in Antarctic summer, followed by near starvation for the rest of the year, may favor larger, more starvation-resistant bodies. P.B. Best, in a 2016 study analyzing 3,302 pregnant adult female sperm whales from Soviet whaling expeditions, found that the latitude size gradient in that species tracks differences in prey availability rather than water temperature directly. Larger squid species are positively correlated with latitude in the southern hemisphere. Animals feeding closer to Antarctica get more energy per dive. They grow larger because they eat better, not because the water itself has a specific physiological effect on their growth. No single mechanism accounts cleanly for all the species that show the pattern. The 2020 Woods and Moran synthesis is currently the most comprehensive treatment of the hypothesis landscape, and its conclusion is unambiguous. The field has no dominant single-factor explanation. The sperm whale. Physeter macrocephalus is the largest toothed predator alive. Adult females typically reach 10.5 to 12 meters and about 11 tons. Adult males typically reach 15 to 18 meters and 35 to 45 tons or more. The maximum reliable straight-line measurement for a male, based on modern re-evaluation of historical whaling records, is around 18 to 18.3 meters. Historical reports of 23 to 27 meter individuals were almost certainly curvilinear measurements taken over the body's curve, or outright exaggeration. The popular framing goes, Antarctic waters produce the largest sperm whales. The largest individuals are found near the pack ice. The actual evidence is more specific than that, and more honest. Sperm whales have one of the most extreme patterns of sexual segregation of any mammal. Females and juveniles live predominantly in warmer, lower latitude waters. Adult males, as they mature over decades, migrate progressively to higher latitudes, subarctic, subantarctic, sometimes right to the edge of the pack ice. Antarctic waters are occupied almost exclusively by large adult males. Females are essentially absent. So when large sperm whales are observed in Antarctic and subantarctic waters, they are large adult males who migrate there, not animals that became large because of Antarctic conditions. The demography is doing most of the work, not the latitude. But that isn't the end of the story. Best's 2016 study, the 3,302 pregnant adult females from Soviet pelagic whaling expeditions between 1961 and 1975, is the strongest quantitative evidence for a genuine latitude-size gradient in sperm whales. The data set is large enough to control for expedition effects and ocean basin. Average body length in pregnant females decreased systematically from south to north in all three major ocean basins examined, approximately 200 centimeters from southern to northern catches in the Indian Ocean, all statistically significant. Females feeding closer to Antarctica are measurably larger than females feeding near the equator. Best's proposed mechanism is McNabb's resource rule. Geographic differences in prey size drive geographic differences in growth. High-latitude southern ocean waters support larger squid species. Better prey quality at southern latitudes produces larger females, not any direct chemical or physiological effect of cold water. For a mammal that breathes air rather than extracting oxygen from seawater, the oxygen temperature hypothesis has no direct applicability regardless. For male sperm whales, the regional size data is murkier. A 2024 analysis of International Whaling Commission catch records found that although regional mean length differences are statistically detectable, they are likely more attributable to catch biases rather than a diagnostic difference in size between populations. High-latitude grounds were specifically targeted for large males. Whalers operated under legal minimum size limits with economic incentives skewing the catch toward the biggest animals. Some Japanese IWC catch data from this period carries documented length distributions that are biologically implausible. And sperm whales continue growing for decades after sexual maturity, which means regional differences in mean length may reflect regional age structures more than intrinsic growth potential. The defensible claim is this: the latitude size gradient is real and well documented in females, and is likely driven by prey resources rather than any direct physiological effect of water temperature. The large male sperm whales of Antarctic and subantarctic waters are large because they are old, experienced animals who migrate there to feed, not because Antarctica grows larger whales. Before concluding that cold and deep means large, the counter-evidence demands equal time. Craig McLean, a body size researcher, has put it plainly. Prominent patterns of body size exist in the deep sea, including conspicuous cases of both gigantism and dwarfism. Both, in the same habitats, sometimes in the same taxonomic groups. The abyssal plain, the vast flat bottom of the ocean between 4,000 and 6,000 meters depth, does not reliably produce giants. The food available there is primarily marine snow, a slow, diffuse drift of mucus, fecal pellets, and fragmented organic material from the water column above. This is chronic energy limitation, and chronic energy limitation selects for small bodies. Mean individual body weight in deep abyssal benthic faunas is often an order of magnitude lower than in shallow water faunas. Most deep-sea organisms are smaller than their shallow water relatives, not larger. McLean and colleagues, publishing in Journal of Biogeography in 2006, described what they called an island rule effect for deep-sea gastropods. Small-bodied shallow-water gastropod species tended toward larger sizes at depth. Large-bodied shallow-water gastropod species tended toward smaller sizes at depth. Body size in the deep sea converges on some intermediate ecological optimum shaped by local food supply and competitive dynamics, not simply pushed upward by cold and pressure. Gigantism and dwarfism occur in the same phylum in adjacent habitats. The Antarctic amphipod data makes the same point from a different angle. Chappell and Peck's 1999 dataset showed that Southern Ocean amphipod species are disproportionately represented among the largest members of their genera compared to tropical species. A real difference. But the majority of Antarctic amphipod species aren't giant. The fauna isn't dominated by oversized animals. Giants are a documented minority, not the norm. Bergman's rule itself holds less reliably than its popular reputation suggests. The original 1847 formulation described a tendency in warm-blooded species. A large-scale analysis of 952 bird and mammal species, the group Bergman was actually describing, found that temperature explains less than 10% of mass variation for most species, with correlations frequently non-significant even within endotherms. For ectotherms, multiple reviews find the rule absent, reversed, or inconsistently supported across lizards, amphibians, and many fish groups. The paleontologist Gerard Vermeer, reviewing the history of gigantism in 2016, argues from a different direction entirely. The largest animals in all trophic and habitat categories tend to maintain high body temperatures, either by generating internal heat or by living in warm environments. The blue whale, the largest animal in the known fossil and modern record, isn't a cold water specialist. It feeds heavily in polar waters seasonally, but ranges globally. Its size can't be attributed to Antarctic conditions. Oxygen minimum zones complicate the oxygen hypothesis from yet another angle. These are persistent layers in the water column where dissolved oxygen drops to 0.5 milliliters per liter or below. Large animals live within and adjacent to these zones using specialized adaptations. Their existence doesn't disprove the oxygen hypothesis on its own, but it does mean that low oxygen does not uniformly produce small animals, and high oxygen does not uniformly produce large ones. So the honest summary of what the evidence actually supports: the coldest, most oxygen-saturated, most seasonally productive marine environments on Earth do produce some of the largest animals in several unrelated taxa. The colossal squid captured in the Ross Sea in February 2007 grew to 495 kilograms in Antarctic water. Giant isopods cluster most densely in the coldest reaches of their depth range. Colossandized sea spiders reach 70-centimeter leg spans in Antarctic water that are simply not achievable in temperate zones. Female sperm whales feeding closer to Antarctica are up to 200 centimeters longer on average than females feeding near the equator, most plausibly because the prey is larger and more calorie-dense. 3 explanatory families have been doing most of the work for 25 years: oxygen availability, metabolic rate effects on growth duration, and the quality and quantity of available food. All 3 have partial evidential support. None accounts cleanly for all observations across all taxa. The 2020 review by Woods and Moran is currently the field's most comprehensive synthesis, and its honest position is that no single dominant mechanism has emerged. What does seem increasingly clear is that food resources at high latitudes carry substantial explanatory weight that neither the oxygen hypothesis nor temperature effects alone can match. It matters that the Southern Ocean's seasonal bloom delivers abundant, large-bodied prey. It matters that a female sperm whale feeding on the large neritic squid of the Antarctic margin will outgrow one feeding on smaller equatorial species across decades of life. The water is cold, the oxygen is plentiful, the predators are fewer, and in the most productive seasons, the food is exceptional. These factors probably reinforce one another, weighted differently in an isopod versus a jellyfish versus a whale. Nobody has fully solved this yet. The pattern is documented, the full mechanism is still being written. Somewhere in the coldest water on Earth, that combination has been quietly building giants for millions of years, and the researchers trying to explain exactly how are still at work.